Yeah. Hi, I'm Venkatesh Bhatt. I work as software engineer at Julia Hub. Me and along with Brad Carman, who is director of consulting services at Julia Hub, we are here to present a talk about all the updates that native DSL of Modeling Toolkit has. Just after Mike told everything that it lagged and why we have JSML, and also give update on standard library, the conventions it has adopted, and etc. Brad has a lunch and learn right after this, so I'll be presenting it completely by myself. You should all attend the lunch and learn after this. Uh, so Modeling Toolkit Standard Library is sort of, it has fundamental components already written out. So you can just use those to build out the composite systems. It has mechanical, magnetic, thermal, and electrical components which are based off similar to Modelica standard library. It has all these components written out. Uh, so recently we have updated what are the conventions that we are following in our connectors. So generally for every domain, there is a connector. You have a through variable and an across variable. Through variable is, it should be a time derivative of some sort of conserved quantity. And the conserved quantity itself should be expressed by an across variable so that you have an energy dissipation equation and a flow equation. For electrical domain, this would be voltage would be the across variable and current would be the flow variable. It gives out one equation at the end if you build out the system with resistor and a capacitor and a ground. And that's why our electrical domain will have voltage and current in its connector. In the translational domain, we have departed from Modelica standard library. Instead of a position and a force, we are using a velocity and a force. Here, if you write out similarly for the damper and mass and a fixed as a ground, then you would get a single equation that you have to solve, which links the force and the velocity. So we get both the we get to solve that. We also have translational position domain. If in case you do still want to use similar to, whatever is similar to Modelica, then we have equation for position and force. And if you write out similar model for figuring out what equations it's solving one that connects position and velocity, and one more the energy dissipation equation. So the comparison between these, the numerical difference between the velocity that you would generate with these two connectors is very negligible. So at the end of the day, based on what your model requires, if it already requires a position variable and if your model needs that, you can just go with translational position, or you could stick with translational. One more difference would be that translational connector, you would need to initialize less number of starting variables because there are less number of variables there. And then the another thing that we added was sign convention. We swapped out a little bit there. The idea is whenever there is an input component like a constant force, and you connect it to a conserved component like mass or capacitance, then the direction, the positive value of flow, whenever it is flowing out, then the accumulation of the conserved quantity should increase. So if you see in the equation, flange has a negative force. That is, force is now flowing out of the constant force. And then when you connect it to mass, it is increasing the velocity, the conserved quantity of that mass as time progresses. So now entering, so these were the conventions that we wanted to update you on. And then now updating about the second part of this talk is about all the updates that we have done for the native DSL of Modeling Toolkit. MTK model already supported parameters, variables, components, and equation blocks, but it was limited in its capacity, and it couldn't do things like arrays, or it couldn't really have looping statements, and etc. Along with those, we have added new blocks for specifying defaults and guesses. This is similar to just passing defaults and guesses to the ODE system. You can have variable and value pairs listed out, and that gets passed to the OD system while it is building. Currently, you can't specify it as a keyword, so whatever you are specifying here will be the override. So if a user is giving input values for these, those will not be accepted, and only the final whatever is hard coded will be passed. This will change soon, where default and guesses can also be a keyword, and you can pass those as dictionaries to the component. Along with this, there was one issue that arguments could not always had to be symbolic in nature, but sometimes when you want to specify, say, length of an array, or you want to set Boolean flags and etc., that would be a problem. So we have introduced something called structural parameters. These are not added to the ODE system, but these are used to influence the structure of the component itself, what you want to add and what you don't want to add. For those kind of things. I would like to start building mass component and side by side just to showcase what we are using, so update is seen. So now MTK model also supports conditional statements. If you want to have a gravity component element for your mass, then based on that you can add the parameter g and also influence the equation how it is written out. Here, one thing to note is you cannot have symbolic parameters as the condition, because these are executed while defining the OD system itself. So these have to be a structural parameter. That's why that whole keyword was introduced. If it makes sense to club all these together, you can also club within an equation within a condition itself. We also want to specify position of the mass. So whenever based on the position condition, you add position variable and also an equation that links it with the velocity of the mass. So to take it forward, for the next step, I would like to build out a composite model of a train and stopper system. The QR code has the relevant docs where you can read out the whole model and optimization of that and such. So here, the idea is we connect train cars with couplers, and you have a stopper. Whenever there is a contact between the train and the stopper, train comes to a halt after some point. So whenever you're building out a composite model, you would have some repeating element in it. So you can have partial blocks defined out. Here, two flanges, which has as the name suggests, it has two flanges. If you have equations, components, just like any other MTK model, you define them all, and then you extend that in whichever model you want to extend it in. Here, one thing to note is if you have arguments that you want to pass, then you have to specify while extending that component. Anything that is defined while extending, that is added directly as an argument of the MTK model. Of the base model that is of train car. So flange A and flange B.V both will be added as an argument. You don't have to dot access it as two flanges dot flange A or whatever. That's a departure from how the components are, variables inside a component, subcomponents are accessed and versus of a base system. Let us add a mass component to the train car. Here we are also declaring where the position A and B, that is starting and ending point of that train car would be. And we connect out a flange A and B, which is for connecting to other components of the train. So train car coupler is a composite model of spring and damper. Instead of building them out from scratch, I'm using from the mechanical translational library. I'm adding a spring constant, a damping coefficient, and a starting velocity of the coupler. These can be set by user as it is declared in the parameters. These are also added as an argument, so user can just pass it. I am defining a subcomponent spring and a damper, and also specifying how these spring and damper connect with each other. And if you build out the train car coupler model and you expand all the connections, and if you see the full connections, it gives out how these spring and damper equations are connected, and everything is just added the whole acausal modeling's advantage shows out, and we don't have to write the entire model from scratch. Moving on to the building train. Even train, we do specify a initial velocity, and then we specify a spring constant to it and a damping coefficient, and we define bunch of subcomponents for train car and coupler, and we give out a mass of suitable range, and then positions are defined according to where it should come in the train, something that makes sense. And then you go on connecting cars with couplers one by one, so that it is all connected, and the train equations get built out. And if you plot out the displacement of this, you can see that there is a constant velocity. They all line up, and the model actually instantiates correctly. For defining a stopper, the stopper would have to exert that amount of force. Again, stopper also has two flanges and two velocities for both the starting point and a force, which is defined according to that equation. I define out how the connectors are equated to these velocities, and how differentials are also connected, equations for that. And when you build out the whole system, the train has an initial velocity. Stopper, I give out a very small spring coefficient and a really high damping coefficient. So stopper brings train to halt quickly. And if you notice, the starting position of stopper is right there where the contact happens for the train. And I ground it with a fixed reference. So we have also introduced a new macro called MTK build. So it basically builds out a system and also structurally simplifies and gives out the equations, the final equations. You can also pass some of the keyword arguments like fully determined, etc., and values to the subcomponent variables as well. MTK model now also supports events. You can define continuous events and discrete events as pairs of equations. To show it in action, if you have a unit mass and friction, I'm declaring that when velocity is 0, there is a you have to treat that as a continuous event. And when you build out the model and solve it, the whole thing just works. Yeah. Thank you.
Great. We have quite some time for questions. Any questions? Right. Yeah. Got you.
Yeah. You had the train car model with like the multiple wagons, the multiple cars. Can you now write this in a for loop to have n cars instead of 4?
Yeah, actually, it can be written out. I don't think components support. Components should support the for loop as well. So you have to individually write out the for loop for the components and separately for the equations. You can't define both together, though.
Okay, so then it would be like components 1 to n.
Yeah, so 1 to 4, you write out a for loop inside the components block to define out how they are, the values according to that should be defined once, and how they're connected will be a separate for loop inside the equation block.
Neat, thank you.
And there's also a composite.
There is a comment from Chris, so can you just speak to the microphone? Yeah, sorry.
Yeah, and there's also, you can use Julia comprehensions as well. So comprehensions are a nice way to kind of do array-like things as well. And there's a comprehension syntax that is also supported inside of there.
Thanks very much for the call. for the talk. Where I work, I do a lot of things that is continuous and discrete. For example, the embedded software in a computer is discrete. And sometimes you have to run a real complex algorithm and so on. It's just one by one representation of the embedded software. How far, or is it already possible to use MTK to simulate these things, like using callback? And if something triggers inside this callback, it changes the dynamics? Is it possible to do this?
Yeah, there are discrete and continuous callbacks that you can define. You can either specify them within the continuous events or discrete events, and if you are writing out as just Julia function, even then you can pass that as a pair of equations for what conditions should be met and what should be the effect because of that to the ODE system while building out.
Yeah, and I do want to mention a few things here. So one thing to mention is that Frederick will be giving a talk on hybrid systems, and he'll go into a bit more detail on the current state of Modeling Toolkit for hybrid systems. And so please check that one out. I mean, he comes from a robotics background. Actually, came from cognibotics before, right? So his big thing has been how do we make it so that way complete control circuits can work with this, right? So there's that going on. There's the state machine integration, right? So Modeling Toolkit support of full state machines as part of its compilation process. And then there's a lot of other things that are required. So I would say that we're not all the way there with hybrid systems yet. In fact, one of the things that we really need to make sure that we're doing is, for example, composition of event systems. So for example, if you have multiple discrete events, it lowers it to multiple discrete callbacks right now, right? If you kind of know the differential equation syntax, right? But what we should be doing within the compiler, for example, is we should be combining them into one discrete callback that is the understanding, you cannot have this, and this happen at the same time, so we can compose these checks and lower it to much more efficient code. Some of these more efficient compilation processes have not been done yet on hybrid systems, but this is a very big topic within Julia Hub right now, and so we are going to be doing a lot of work on the Modeling Toolkit compiler with that. Another aspect as well is the connection between structural simplification and hybrid systems, right? Because, for example, if there's a variable that you only have within a event, you don't want your DAE simplifier to delete that variable because it realizes there's no equations on it. We need to do a few things within the event, within the simplification engine to be able to better support those kinds of use cases. So there's a lot going on with hybrid systems. There's a lot that's working well. There's still some things we need to do in the compiler, and it's one of our main priorities over the next year.
Thank you very much. Are there more questions?
This is more of a also reply to that, which is specifically for changing equations within callbacks. One very well-tested way that works for doing that is you can introduce a parameter that's either like true or false, and then have an if-else that has both sets of the dynamics. And so that way you can have both parts of the dynamics in the system, and then they'll be changed by the callback. And one of the really nice things about doing it this way is that your model is continuous, so the ODE solver doesn't see the fact that at a certain point everything suddenly changes, and that will happen outside of the solver loop in the callback purely, and so you maintain your continuity and higher derivative smoothness that you want for your solvers.
More questions? Yep. Or comments?
Since we discussed a lot of these different pieces, Chris, maybe do you want to just mention how can one get to all these pieces and download them and try them out?
Yeah, so everything to do with Modeling Toolkit Standard Library and such. You can find all these with if you go into the Modeling Toolkit Standard Library documentation, right? So you go to the SciML docs and you'll find that there's a whole section that is just about the modeling tools, and you can find all that. But there's also a lot of these extra compilers, a lot of these extra component libraries and such. So if you search on JuliaSim, you'll find the JuliaSim documentation, and this gives you the whole world of extended standard libraries, extended component libraries, and then also the extra compilers like the JuliaSim compiler, which is where a lot of things like these state machines live as well. So there's a huge ecosystem that's growing, and definitely because of the way that it's growing in so many different ways, we plan to be working on the websites to make sure it's much more easy to discover everything that's going on. But yeah, so there's just so many contributors and so much work going on that we will be working a lot more on that discoverability in the near future as well.
All right, unless there are more questions, I suggest we wrap it up. Let's thank our speaker again. Yeah. Thank you.